Hi guys, it's Professor Connor. I wanted to send you this video because a lot of you have had questions on some of the problems in the post lab. So I wanted to go over that before the deadline tonight. I was going to have it for you yesterday, but I had issues with my computer. So I'm just going to go over how to calculate those two problems in the post lab and then kind of go over how pH works. So hopefully this will help. It will answer questions that you have. And again, still, I have a few emails that I have just seen. So hopefully this answers those. And then if it doesn't, I will go back in and respond to your emails after this video is complete. But I wanted to go through the math. So to do that, I'm going to go ahead and share my screen because I actually have them all ready to go. So here is your post lab. So the two questions that I'm going to basically go over is 3 and 6. Before I do that, however, I want to go over the bottom question. It asks you what the most effective buffer is and what the least effective buffer is. So a buffer, as we know it, is something that actually will keep the pH at a certain level the entire time. So we have buffers in our stomach that if we're at a 2, the buffer will keep it at a 2 and it doesn't move it. So the best buffer, the most effective buffer, keeps those pH levels even out where they don't change. So if you're looking at this down here, it has a buffer in there for you. So honestly, this kind of drives me a little crazy. These assignments are given to us by our lab directors. They have the buffer in there kind of as your positive control, right? So this is what it would look like if you actually had a buffer. So 7 to 7 doesn't change, doesn't move. It's a great buffer, but we expect it because it has obviously the word buffer in it. So it doesn't, it's effective because it acts as a buffer. So we're looking at the other two, and if we're looking at water and we're looking at skim milk, the skim milk stays the same no matter what we do, right? After adding acid, the skim milk still is at a 6. So it is the best buffer out of the two, water and skim milk. So the most effective buffer besides the buffer itself, the phosphate buffer, would be your skim milk. It's important to remember that. And then of course, if you're looking at water, it starts at a 7. We put acid in it and it drops to a 2. So obviously water is the least effective buffer in that group of materials. And so again, the positive thing about this is you can see that if you see buffer, you can see that it didn't change. So that kind of gives you that clue. But when we're talking about the other materials or the least and the most effective in this assignment, in this piece, you're looking at the difference between the water and the skim milk. So with that being said, let me just get right into question number 3. The soft drink Mr. Pibb contains most, among other things, 39 grams of sucrose in a 355 milliliters of solution. They want to know what the molarity of the sucrose solution is and what the percentage or what percentage the sucrose is in the solution, which is the weight divided by the volume. So for you who might still be a little confused, I have actually written it out. Hopefully it works. I have all these things. Sorry, I have to get rid of a couple things. It just is weird. Okay, so this is the one that is number 3. So it's saying, and I'm sorry if you can't read that very well, hopefully you can see it. So we want 39 grams of sucrose and we have it in a 355 milliliter solution. They want to know what the molarity is. So that is actually, molarity is moles per liter. And they also want to get the percentage of the solution, which we already know down here is the volume or the weight divided by volume. So to find out how many grams are in a mole of sucrose is the most important thing because we need to figure out what percentage of the mole that we have with the 39 grams. So the way that we do that is we look at the periodic table. And if you look at the periodic table, you're looking for that bottom molecular weight number. So the periodic table in this case shows that C, so we're looking at the molecular formula for sucrose, which is C12H12O11. So we have to break that down to get the molecular weight for each one of those pieces. So every time we look at this, we're looking at 12 atoms of carbon, 22 atoms of hydrogen, 11 atoms of oxygen. So that's the weight or how many of those hydrogen or those atoms are there. So for the periodic table, we looked it up, is C is 12 grams, right? Hydrogen is 1 and oxygen is 16. It says 15.999 on your periodic table, but we rounded up. So then I have to look at that formula and say, okay, I have 12 carbons, but each one basically, if we're going to say weighs, or there's a certain number of grams. So there are 12 grams per every carbon, so we have to multiply that 12 by 12, and we get 144. The hydrogen is 1.009 on the periodic table. We're rounding it to 1, but there are 12 of them, so we have to account for all 12, so we get a 12. And then oxygen is, again, that 15.999, but we round it to 16, and we have 11 of them. So we're going to do 16 times 11, and we get 176. And because this is a combined molecule, we have to add all those pieces together, and we get 342 grams per mole. In our solution, we only have 39. So we have to figure out how much of that mole we actually have in our Mr. Pibb. So we have to do 39 grams divided by the total of moles per liter, which is 342 grams. That's how much you would get in a mole if you were measuring it correctly for 1 mole, but we don't have 342 grams, we only have 39. So we only have 0.11403 grams per mole. So we have a percentage basically of that 342. So now we have to figure out molarity, right? So molarity is equal to moles per liter. We have 355 milliliters, not quite a liter, so we have to figure out what that is in liters. So 1 liter equals 1,000 milliliters, so we have to take our lovely 355 and divide it by the total amount of liters, which in this case has to stay in milliliters for now until we can transform it over to liters, which we do. 355 milliliters divided by 1,000 milliliters is 0.355 liters. In other words, we don't have a full liter. We have a percentage of it. So now we're going to do molarity, which is moles per the solute divided by liters. So our moles per the solute is this number up here. That's how much we have in that Mr. Pibb. That 39 grams is equivalent to 0.11403 grams per mole. And then we have our liters, which we calculated here. So it's 0.355 liters. We divide those and we get our molarity, which in this case is 0.32. If they asked us for something like our other things, it doesn't disassociate, it stays together. So if we were doing other numbers with that, we would figure out that number we're not doing. So, if we were doing, we would look at, if we were doing and figuring out how much we could break that down, and then that would change for something different. So number 2 in that problem is asking for the percentage of sucrose in the solution. So we're taking the weight, which is 39 grams, and we're dividing it by the volume, which is 355 milliliters. So our percentage is 11.6. It's just a straightforward division problem. So hopefully this makes a little bit more sense. It has a few more steps, right? The basic gist was given in the PowerPoints, but this kind of is broken down, and I hope in a way that you can understand it a little bit better, or now it's starting to click. So the other part of that assignment was this one, this question on the bottom. How would you prepare 500 milliliters of a 0.1 molar solution of magnesium sulfate from a stock solution of 2 molars of magnesium sulfate? So the first thing we're looking at is we're doing a diluted process. So we're diluting one from the other. The tricky part is figuring out the wording in the question. So if I am saying, how do I prepare? That means I'm getting to that point. That's going to be my end solution. So if I'm looking at preparing, then this part of the equation, that's what I'm trying to get to. And we're working from a stock solution of 2 molars of that magnesium sulfate. So I'm setting out my formula. V1M1 equals VFMF. So this is volume initial times mass initial, or molar solutions initial, equals the final volume and the final molarity. So I have broken down the question. If I'm preparing 500 milliliters of 0.1 molar solution of magnesium sulfate. That's my end. And then from the stock solution, 2 molars per magnesium sulfate, that's the beginning. So that's what I'm starting with. So I have written this up where I put, here's my start. This is the side I'm starting with. This is my end result. V equals volume. M equals the molarity of that solution that we're starting with. And now we're just going to plug in the numbers. So it should be pretty easy, hopefully. We don't know the volume of our initial solution. So that is our unknown. So we're going to give X to that. So I've taken V1 and I have made it the X, the unknown, and then I've plugged it in here to this part of the solution. And then I just plugged in my numbers. So I know I start with 2 molar solution that I don't know that volume, but I end with 500 mils times the 0.1 solution. And then you just need to get you need to get the X on one side by itself, and that will give us our final volume, or the initial volume that we have started with, sorry. So I just do the math. So the M's are crossed out because they cancel each other out. 2 and 2 makes it 1, so we get X on this side by itself. We divided it to get X alone by itself, so it becomes just an algebra problem. So now what we do to one side, we have to do to the other. The molarity cancels out. So now we just take 500 times 0.1 divided by 2. This is 50. This is divided by 2, so it ends up being 25 mils, which is now our initial volume. So this number is actually what we started with up here. So it's that X, the volume of the initial solution that we were looking for. Hopefully this makes a little bit more sense. I'm trying to hurry so I can get this out to you guys today. But I hope that that kind of helps clarify some of the pieces that you're looking at, and answer some of the questions on here for you. One other question that I've had this week is this one, number 5. It says, suppose the concentration of H plus in solution 1 is 10,000 times greater than solution 2. So when we're talking about an acid, the more H plus or hydrogen ions that you have, the more acidic it becomes. So if you see that H plus, the more you have of that, the more acidic it is. So the volume, or the numbers in acids and bases, 1 is most acidic. The bases, 14 is the most basic. And we're looking at that particular chain of calculations. So if the H plus is 10 times or 10,000 times greater than solution 2, we can assume that solution 1 is super acidic and solution 2 is moving up towards the basic area or even the neutral zone. That also means that every time that you move from, say, a 1 measurement in pH to a 2 measurement, it's 10 times greater than what it is from 1 to 2. So that's what the measurement is. So if I'm going from 1 to 2, it's 10 times more acidic at the 1 than it is at the 2. And so if I go up another section to 3 and 1, 3 is 100 times more basic than that 1 sitting at the bottom of the acidic realm. So hopefully that makes sense. And it makes a little bit more sense because there is a question on the quiz that's similar to that. So just keep that in mind. I think that's pretty much it. Again, let me just stop sharing my screen. All right, so hopefully that helped. If you have more questions, if you're still struggling, you can email me. I'm going to look through my emails again one more time. I haven't had a chance in the last hour because I was doing this, to look through any emails coming in. So hopefully this will help as you're working on that post lab, and hopefully it makes a little bit more sense on how that works. And then hopefully it will help when you're doing the quiz today. If you've already submitted your post lab and you're going, oh my gosh, I got it wrong, I didn't understand it, you can resubmit. You can resubmit all the way up until tonight. And you know, just, I can see your most recent submission, so it doesn't matter if you submit 5 things. I can see all of them, so it doesn't disappear. It doesn't make the other parts disappear. So if you want to redo it and make some changes, absolutely do that. Other than that, I hope you guys are doing well. Remember, everything is due tonight. Next week, we're going to have some McGraw-Hill Labs back. This week we didn't have any. I know y'all were kind of like struggling on, hey, there's no labs in the McGraw. I realize that. But next week they're coming back. And I hope you guys are doing well and staying safe. And again, if you need me, please email me. If these aren't enough for you, or if you're not able to go to any of the office hour times, then I am more than happy to do a Zoom with anyone. So hopefully that helps. Have a great day and a great weekend, and I'll see you on Monday.